Hello, everyone. I'm Daniel Valmassei, and today I'm going to talk about some of the tools and techniques we use in our lab to do gamma ray spectroscopy. Um, Gamma decay is the emission of a photon from a bound excited state to a lower nuclear energy state. In most cases, beta and alpha decays do not occur to ground states, but rather to bound excited states, so they are often followed by these gamma decays um, in the daughter nuclei. For example, the thallium-208 decay scheme shows many of the excited states of lead-208 decay to the first excited state before cascading to the ground state. Our array is intended for the identification of natural radionuclides who are continually redistributed into the environment by biological, meteorological, and geophysical processes. And these nuclei have very specific decay chains whose signatures can be identified by their gamma transitions. However, they rarely occur in large quantities. That's why we use coincidence spectroscopy. Our array is composed of two sodium iodide scintillators, which produce flashes of light with intensity proportional to incident gamma rays. And the light is then converted to electric pulses by a photomultiplier tube and analyzed by a spectrometer. By using two scintillators and requiring that both record an event within a certain coincidence window, we can drastically reduce the number of events recorded from the background sources such as cosmic ray muons, radon gas, and the detectors themselves, and the other naturally occurring radiation. As you can see on the right, the coincidence requirement removes all the peaks from the background and reduces counts by nearly 2 orders of magnitude. Specifically, our array is well equipped to detect gamma cascade events and the back-to-back 511 keV photons produced by beta plus decay. We prefer this method of background filtering because low count natural samples peaks may be covered by natural background and might be lost with standard background subtraction methods for one detector. This year, I've developed a Python app to control offline data analysis for the array. While we ultimately intend to use the industry standard route, Python is more accessible to students in our department and at the undergraduate level. Some of the features that we've built this semester include variable 8 nanosecond to 40 nanosecond coincidence windows, 2D histogramming, one detector projections of the 2D histograms, standard background subtraction for the little that you saw in the last slide, coincidence gating, and peak fitting, or Gaussian peak fitting. So after data from the detectors analyzed with the offline filter program, we can histogram the events according to their energy in each detector. For example, on the left, an event with 1275 keV gamma and in channel 0 and a 511 keV photon in channel 1 would be plotted inside the red oval. Then the events can be projected down to either axis to reproduce a more familiar spectrum, as you can see in blue on the right. So those spectra are just a series of points, and our sodium iodide detectors our scintillators are fairly efficient, which is advantageous for our coincidence conditions. But the high efficiency comes at the cost of lower than ideal resolution. Therefore, we have to fit our peaks to Gaussians in order to characterize the spectra completely. On the left, you see a high counting sample, which usually conform easily to the Gaussians and which might be easy to analyze without peak fitting. But on the right is lower counting sample, or a lower counting run rather. The spread of the points makes the peaks more difficult to analyze discretely. But their agreement to Gaussian suggests that this technique is valuable for estimating the peaks, widths, heights, and centers for the low counting samples we expect to explore in the lab. So all of these tools have helped me this semester in characterizing the efficiency for array and comparing it to a JAOT4 simulation built by Aiden last year. When detecting without coincidence conditions and with poorly known sources, the experiment is almost within error of the simulation, though it trails off at high energy. And though the simulation is not yet equipped to predict coincidence conditions, the efficiency of the array drops by about a factor of 4 when there's online coincidence filtering. So thank you very much for listening. And if you'd like to hear more about how we use these techniques in the lab and maybe see some more interesting results, be sure to listen to Pranjal Singh's presentation later this weekend.